Hey y'all! Today we're going to talk about martingales. Martingales are a useful tool for analyzing random processes. We're going to define them in this video, and in the next video we'll see how to use them to prove the Azuma-Hufting inequality, which is kind of like a Chernoff bound that can work even on dependent random variables. Cool. Let's get started with the definition of a martingale. Let z0, z1, ... be a sequence of real-valued random variables, and let x0, x1, ... be a sequence of some random variables not necessarily real-valued. We say that the sequence zt is a martingale with respect to the sequence xt if the following things hold for all t. First, zt should be some function of x0 through xt. Second, the expected value of zt, or its absolute value, should be finite. And third, the expected value of zt conditioned on x0 up through xt minus 1 should be equal to zt minus 1. As a simple example, suppose that xi is the outcome of a random coin flip. So xi is either heads or tails. And let's say you're playing a gambling game where if you flip heads, you win $1, and if you flip tails, you lose $1. So let's suppose you start with $0 at time 0, and let's let z sub t be the amount of money you have at time t. And it's okay if the amount of money that you have is negative, that just means you're in debt. Now I claim that z sub t, this sequence, is a martingale with respect to the x sub t's. Let's see why. So first, z sub t is definitely a function of x0 through xt. How much money I have at time t depends only on the coins I flipped so far. Second, the expected value of xt is certainly finite, can't be bigger than t. And now let's check this third thing. We have that the expectation of zt conditioned on x0, x1, ... xt minus 1. Well, this is just equal to however much money I had at time zt minus 1, since I'm conditioning on all of the previous coin flips, plus the expected amount of money that I get on the tth flip. But this here is just 0, with probability a half I gain $1, and with probability a half I lose $1. So this whole thing is equal to z sub t minus 1 as desired. So this is a martingale. Some quick martingale terminology. If we let yt be equal to zt minus 1, then this sequence of yt's is called the sequence of martingale differences. Also, if xt is a martingale with respect to itself, that is, if xt plays both the roles of zt and xt in the definition down here, then we just say xt is a martingale, period. One reason that martingales are a useful concept is that we can obtain a martingale from basically any real-valued random variable. This is called the Doob Martingale. To see how this works, let's let a be a random variable, and suppose that x sub t is a sequence of random variables defined over the same probability space as a. That is, it makes sense to say things like the expectation of a conditioned on the x of t's. Then the Doob martingale of a, with respect to the sequence xt, is defined to be the sequence zt, which is given by zt is the expectation of a conditioned on x0 up through xt. We'll see a few examples of this in a minute, but first let's verify that this is indeed a martingale, at least assuming that the expected value of zt is finite. Okay, so if we make that assumption, then definitely zt is a function of x0 up through xt. So now the first two criteria of a martingale are satisfied. So let's check the third one. We need that the expectation of zt conditioned on x0 up through xt minus 1, so this is supposed to be equal to zt minus 1. So by definition, this is equal to the expectation of a conditioned on x0 up through xt, conditioned on x naught up through xt minus 1. Now this outer expectation is basically going to integrate away this x sub t here. So what we're left with is the expected value of a conditioned on x naught up to xt minus 1, which by definition is equal to z sub t minus 1. So indeed, this is a martingale, or at least it satisfies the third property. So here we used the fact that for any random variables x, y, and z, the expectation of x conditioned on y and z conditioned on y is just equal to the expectation of x conditioned on y. So there wasn't anything special about this being a sequence or anything like that. This is just true for any triple of random variables. And again, basically what's going on here is that this outer expectation sort of integrates away this other variable z. So let's see some examples. One common way to use a Doob Martingale is to analyze a random variable where we think of information about that random variable as being sequentially revealed. So for example, maybe the random variable you care about is the number of empty bins at the end of the day if you're dropping balls into bins, and more information about the value of that random variable is revealed every time you drop a ball into a bin. To work this out a bit more formally, suppose we have m balls that we're dropping into n bins, and let a, our random variable, be the number of empty bins after all m balls have been dropped. Now let's let x sub t be the location of the tth ball. So if the first ball lands in this bin, then x sub 1 will be this bin. Then zt, the Doob Martingale by definition, is going to be equal to the expected number of empty bins at the end of the day after I've dropped all m balls, conditioned on the locations of the t balls that I've dropped so far. Observe that z naught here is just going to be equal to the expected value of a. So this is just the expected number of empty bins if I have no information whatsoever. While zm, the last one of these, is equal to the expectation of a conditioned on x1 up to xm. And this is the actual number of empty bins after all of the balls have been dropped. So this martingale kind of interpolates between the expectation of this random variable and sort of the random variable itself. As a second example, let's look at the edge exposure martingale. Here, let's let G be an Erdős-Rényi random graph with parameters n and p. So that is, we have n vertices, and each edge in the graph is present independently with probability p. Now let's let A, our random variable, be the chromatic number of G. That is, the minimum number of colors needed to properly color the vertices of G. That is, coloring the vertices so that no two adjacent vertices have the same color. Let's let x1, x2, up to xn choose 2 be random variables defined so that x sub t is equal to 1 if edge t exists, and 0 otherwise. Then the Doob Martingale, zt, with respect to x1, x2, ... is by definition the expected value of a, the chromatic number of G, conditioned on x1 up through xt. So that is, this is the expected chromatic number given the status of edges 1 through t. So to draw a picture, we've got n vertices here. And we're thinking to ourselves, okay, what do I expect the chromatic number of this graph to be? So I have some expectation in mind. And now I say, aha, this edge exists. How about now? And then I'll update my expectation. And then I say, aha, this edge does not exist. How about now? And then I'll update my expectation. This edge exists. How about now? And so on. At the end of the day, we're just asking, what is the expected chromatic number of this graph, given all of the edges being the status that they are? This is called the edge exposure martingale because we're sort of exposing whether or not an edge exists one at a time. A related example is the vertex exposure martingale. So we can set this up in exactly the same way. G is going to be an Erdős-Rényi random graph, and A is going to be the chromatic number of G. But now, let's let y1 ... up to yn be random variables defined so that y sub t is equal to the neighborhood of node I. That is, y sub t can take on 2 to the n minus 1 possible values, which say which of the n minus 1 edges connected to I are present. And as before, we can define zt to be the expected value of A conditioned on y1, y2, ... up to yt. So now the picture looks like this. We have our n vertices, and we ask ourselves, what is the chromatic number of this graph in expectation? We have some expectation in mind. And now I say, I'm going to tell you all about the neighborhood of this vertex. This vertex has these edges, let's say, and not these ones. Okay, now what do you think about the chromatic number of this graph? What's the expectation conditioned on this having happened? So this is called the vertex exposure martingale because we're exposing vertices one at a time. Okay, so in this video, we saw the definition of a martingale, and we saw a few examples. In the next video, we're going to see an application of martingales proving the Azuma-Hufting inequality. Thanks for watching, and see you in the next video.